Okay folks, welcome to lecture 12, and in this lecture we'll be taking a look at the laws of logarithms. But just before we go ahead, we'll just have a quick recap. So in lecture 11 we saw logs were the inverse of power expressions. Logs undo powers, powers undo logs. So this allowed us to go from the language of powers into the language of logs. This statement could be written as the log to the base 10 of 1000 is equal to 3. Or here the log again to the base 10 of 0.001 is equal to minus 3. And we discussed the mechanics of this in lecture 11. Or we could go from the language of logs into the language of powers. 10 to the power of 2 is 100. 10 to the power of minus 2 is 0.01. It's very important at all times, guys, to notice that the base is the same as we transfer from one language, the language of logs, into the language of powers, or vice versa. So this skill, switching off logs or switching off powers as we need to, is very important, because often we'll have an unknown and it'll be a power in an equation like this. So we need to be able to switch off this 10 to the power of. We need to kill this to get x on its own. And how we do that is by using a log with the same base, and we apply that to both sides. Now on the left, these inverse operations cancel each other out, and we get this. Now normally we'd reach for a calculator to solve this out, but in this semester we won't be doing these. But that's the basis. Like, we need this ability to get x on its own when it's sitting as a power term, and we'll use logs to do that. We'll do this an awful lot more next semester. This semester we just really focus on the logs kill powers, powers kill logs. Now we're going to move on to the lecture proper. And just like there was rules for dealing with powers, there's also rules for dealing with logs. So we're familiar with these three rules. In the language of logs, they're pretty much the same rules, but they're obviously written very differently. Here we're multiplying, so we add the logs. In the powers we were multiplying and we added the powers. Here we're dividing two log terms and we subtract the terms. Very similar to with the power statement. And here we have a value raised to a power and we end up multiplying by that value. So we'll just take a look at where these rules kind of come from, and then we'll use them. So say if we have a calculation like this, 100 by 10,000 is a million. So most people would be able to do that even with our estimation skills and stuff like that. If we turn them into the language of powers first, this is what we would get. If we turned into the language of logs, remember we would kill the powers, but remember what's happening here? We add these powers. That's what gave us the 6. So in the language of logs, that's all we'd have to do. 100 to the base 10 is 2. 10,000 to the base 10 is 4. And when we add them, we get 10 to the power 6, which is a million. So you can see the maths is a lot simpler in the world of logs. Then we'd actually use our anti-logs to convert this back, and that's what would give us our answer there. So we switch into the language of powers to do the problem, and then we switch back out to give us our answer. We would normally call these the anti-logs, just back in the old school. You guys wouldn't call them that, but I might often refer to them as anti-logs. It's really 10 to the power of. Similar problem, 10 to the power of 2 divided by 10 to the power of 4 gives us 10 to the power of minus 2. If we were to look at this in the language of logs, it's simply 10 to the power of 2 minus 10 to the power of 4. We get minus 2, and now our answer is going to be 10 to the power of minus 2. This is switching us back into the normal language again, and we get 0.01. So this is just giving us a simple example, guys. There's rule 1. If we're multiplying two values, we simply add their logs. If we're dividing two values, we simply subtract their logs. And finally, if we had to get the square root of 100,000, in the language of powers, there's our 100,000 and there's our square root. And now we multiply these values and we get 10 to the power of 5 over 2. In the language of logs, it's simply 5 multiplied by a half, which gives us 5 over 2. When we want to find our answer, it's going to be 10 to the power of 5 over 2, which gives us the square root of 100,000 is approximately 316.23. So that kind of is hopefully just to give an overview of how those rules work. And you can see that the maths is a lot simpler when we switch into the language of logs. That's all we're doing. So something very complex like this switches into a much simpler problem. So now hard sums have been around a long time, an awful lot longer than calculators. So hard sums didn't appear with calculators, they kind of preceded them by a significant amount. And logs were used by most kids and anybody who was doing maths because they made tedious calculations an awful lot easier. So here, say if we had a number like this and we wanted to turn it into a log, and here's two numbers. We're going to do a few sums with these numbers, but I'm just going to show you where the log value comes from. We would go to our log tables, but we'd only look up the first 3 digits. As the tables get more accurate, you could look up the first 4, the first 5 digits, but the tables I have are a bit rough and ready. So we just look up the 127 and the 891. So here's the 127 gives us 1038, and here is 891, which gives us 9499. Whoops. So there's the first value from the log tables, and there's the second value. There's the first value from the logs, and there's the second value. Now what we do is we take a look. Well, the first value is really, it's not 127, it's 1.27 by 10 to the power of 5, and that power of 5 gives us that value there. Similarly, this value here, it's not 891, it's 8.91 by 10 to the power of 4, and that 4 sits in there. So this value is now representing that number there. If we were to talk about, well, what does it mean? This is what it means, is 10 to the power of this number gives me back my 127, my 127,000. Similarly, this number here to the power on 10 gives me back my original value. But doing maths with these numbers, as we'll see, is an awful lot easier than doing maths with these numbers. So this is where the logs come from, guys. So the first value is telling you in scientific notation what the power on 10 is, and then this is a value for the 127 bit. So just kind of, guys, say if we were looking for what's 8910, because this is 10 to the power of 3, it would be 3.9499. So there's a nice pattern to logs. 891 would be 2.8499. 9499. And say 89.1. Where was I there? 89.1 would be 1.9499. I'm going to get rid of these, I'm writing too low. So that, guys, is essentially where our log values come from. Now, you guys would just hit your calculator. You just hit your calculator and it gives you this number. But at the moment, you don't have calculators. You won't be doing anything with log tables either. I'm just kind of showing you. It helps develop where they come from a little bit better. So now this is my number, the red, and this is my number for this one. And we'll use these in the following pages. So say if we had to multiply these two values. If we were to switch into the language of powers, guys, this is what we'd be multiplying. And we know from our laws of powers that we'd simply add the powers, and that's what it gets us here. In the language of logs, we simply have to add our two values. So there's no multiplying going on at all. When we add these two values, we get this. Now, I know my answer is going to be by 10 to the power of 10. I then go to my anti-logs. Really, that's 10 to the power of values. But I would just look up this 4-digit code here, 0.537. And here it is up here, 1132. And now my 10 to the power of comes in there. And that's my answer there. So all the maths I had to do, guys, was add these two values. And then look up this value in my anti-logs. I know the power on 10. And this is my answer. So once you were experienced with using log tables, that would only take you a minute or less. The real answer, guys, is actually this, if you were to calculate it out. But the percentage error is very, very small. So for the speed at which you could perform your calculations, the level of error was very small. And you could definitely, guys, the tables I'm using are a bit limited. There was more accurate tables out there which would reduce this margin of error considerably more again. So the margin of error becomes negligible. This is what gives us rise to the first rule. When we're multiplying two values, we can simply add their log values. Now we look at division. So with division, same two digits, but now they're being divided. Same two numbers, really, not digits. So if we were to talk about powers, remember when we're dividing powers, we subtract them. So we would subtract those two values. We would subtract the blue value from the red value, and this would give us our power. In the language of logs, which is what we're talking, we simply subtract our two values, and this is what we get. I know my answer now is by 10 to the power of 0. I go to the anti-logs and look up those values, and I get 1.426. By 10 to the power of 0, that is the answer. There's the answer using a calculator. And you can see again the margin of error is very, very small. So with logs, when we're dividing two values, we can simply subtract the two log terms. We look at the third rule now. We'll just find, oh, it's actually the cube root. So sorry guys, should be the cube root there. We're looking for the cube root of this value. And again, now you can imagine trying to do that without a calculator is very difficult. But if we look at the language of powers, this is what we have. And remember, we'd multiply our powers. So we'd essentially be dividing 5.1038 by 3. And that gives us this. In the language of logs, we simply multiply by the power. And that gives us this value. So you can see this sum, guys, just simply getting a third of that value is an awful lot quicker than trying to work that out. We'll go to our anti-logs. So I know my answer is going to be 10 to the power of 1 because of this value. And I'd look up this. Now again, guys, with a calculator, you would just simply key the value in and press the button. Using our anti-logs. So when I say anti-logs, guys, I'm really actually meaning 10 to the power of. It undoes logs, which we know. So there's our answer using log tables. And we can see again the margin of error is very, very small. And the log tables I'm using are a little bit rough and ready, so it would be quite easy to reduce that margin of error significantly again. So what this rule is telling us, guys, is when you have a power raised on a value, we can simply multiply the value by the power. And that's much easier than trying to work out this sum here. So hopefully that just gives a little bit of context to the rules, guys. I'm not going to ask you to produce any of this, but it's just to show you how the rules worked and made maths much easier back in the day. I think you'd agree it's a lot easier to divide a number by 3 than it is to work out a calculation like this. But this is kind of gives us rise to our 3 rules, which I have on the next page. And now we'll start to take a look at some problems. So the problem here, guys, is very often in maths you're going to come across an expression like this. I'm only writing this in so it'll make sense. And it's impossible to switch off the logs in their current form. We need to reduce this expression down to a single log, like I'm just going to do this. And once we have a single log on the left, guys, now we can solve the equation because we can kill the log with 10 to the power of. We get 2x squared is 1,000. And now we can begin to solve out. X squared is 500. So x is the square root of 500. But we can only start to initiate this stage when there's a single log here. We need to use our rules to compress this expression. Here's 2 logs. We need to compress it down so there's 1 log, and then we can solve it out. Again, guys, this stage is going to come next semester. So don't worry about it because you need a calculator to do it. Can't spell semester, so we just leave it. But at the moment, we're just sorting out the mechanics of how we do it. So here, guys, we're looking at our log rules, but we're actually working here. We have 2 logs been subtracted, and we're going to go back the way. So log of A minus log of B can be written as the log of A over the log of B. So there's A, there's B, and we just simply 6x to the power of 4 divided by 2x squared. Numbers do what numbers do, 6 divided by 2, and powers do what powers do. And there's our answer. So that's a fairly easy example. It can get a little bit trickier than that. So now, guys, we've reduced our two log terms down to a single log term. And that's our goal. We look at another one, a little bit more complicated. With these guys, even though it's written, I always do my positives first. So using here, guys, we've 2 log terms been added. So I'm then going to multiply them. So the log of A plus the log of B is equal to the log of A multiplied by B. Numbers do what numbers do. Always keep your log there. 12, 3 by 4 is 12. And then powers do what powers do. Now this guy is waiting his turn. 6x cubed So now we've two log terms been divided, or been subtracted, sorry. So we'll use rule 2. We have log of A minus the log of B. We now divide the two terms. So there's A, 12x to the power of 5, goes on top. The first one always goes on top, guys. And again now, numbers do what numbers do. 12 divided by 6 is 2. Powers do what powers do. X to the power of 5. Divided by x to the power of 3. We subtract the powers. And there's our answer there. Trickier one. Now guys, this is trickier, but the only real difference here is, guys, we have these numbers here in front of our logs. If we take a look at the log rules, guys, there's no numbers in front. We need to clean up the logs first. So we use rule 3. Anytime there's a number in front of the log, we write it as a power. But it's very, very important, guys, to put brackets around this first. So I'll show you what I mean. So here, guys, I'm going to bring this 2 up as a power. So this will be 3x squared all to b squared. Similarly, this 3, so don't bring it up, guys. Don't just write 2x cubed. It's 2x to b cubed. And that is the most likely mistake you're going to make with these. So now the 2 has to get cubed and the x gets cubed. So this guy is unchanged. He doesn't have a number in front of him. But now I've cleaned up all my logs, but I'm just going to write them a bit neater. Both bits, guys, remember, if we have a, b being squared, both bits get squared. So here we have 3 being squared. Be careful, it's not 6, it's 9. 3 squared is 9. X to the power of 2 raised to the power of 2, we multiply the powers. Here, guys, the 2 gets cubed. 2 by 2 by 2 is 8. X raised to the power of 3. That's still x to the power of 1 raised to the power of 3. So now, guys, we'll take a wee look. We're going to do... I'll just do them in the order they're written, just to avoid confusion. So we'd use rule 2. We have a divided by b, so this will be the log of 9x to the power of 4 divided by 12x to the power of 4. So that'll give me the log of 3 over 4 plus the log of 8x cubed. He's waiting his turn now. So sorry, guys, the x to the power of 4s will cancel out, and I just tidied up then the 9 over 12. Now, guys, we'll use rule 1. With 2 log values been added, so we multiply their terms. So this will now be the log 3 over 4 multiplied, 8x cubed, I left that out. 8x cubed. Now numbers do what numbers do. We've 3/4 multiplied by 8, cancel. Going twice, so that'll give me numbers do what numbers do, guys. Sorry, and this just looks a bit messy. I'm going to do it again because it looks too quick. So it's 3 over 4 multiplied by 8 over 1, really. 2, 1. So that, guys, will give me 6. Numbers do what numbers do, gives me the log of 6. And if you think about it, 3/4 of 8 is 6. And then, guys, powers do what powers do. We've only one power. And now, it's very important, guys, as well. This is something students don't often realize, is these are equivalent expressions. So this big expression here is the exact same as that expression there. It's like saying, trying to find a bit of space, 100 divided by 200 is the same as a half. They're equivalent. One is more complicated than the other, but they both have the same value. And that's what we're saying here. This complicated expression on the top can be represented by this much neater expression below. And the lower expression, guys, is much easier to help us solve problems. There's more examples, guys, on the videos in Moodle, so please take a look at those. These are tricky, but it is an essential skill we need for logs, to be able to compress expressions with multiple logs down to an expression with a single log. So there's only one question, guys, on this lecture. So same idea. And just have a go at these three problems here. So to finish up then, guys, we'll just take a look. So make sure you have a go at them, guys, and you can get one of these, guys. I think this one will have a fraction in it, so don't be put off by that. You could write that like this, or it could be 3x squared over 2. Now that's not the answer, but there will be a fraction, I think, in the middle one. So don't be put off by it, just write it properly. Numbers do what numbers do, powers do what powers do. And now, guys, we're just going to kind of push out to where we're going next semester, but we're not obviously going to go there. It's just to give you an idea where we're going. So here's the power expression on the left. Here's the equivalent log expression on the right. And as we build up, 10 to the power 4 is 10,000. The log of that value is just 4. Keep going, the numbers get bigger and bigger. But hopefully you can see, guys, what logs can do is they actually, instead of dealing with very large numbers like this, if we use logs, we can compress them down to a much more manageable scale. And that's one of the reasons we use logs a lot, is to actually compress large ranges of data. And they're so useful at it that they just become embedded in the science of the maths associated with it. So we'll take a look. So in the real world, where do logs occur? One area, 3 areas, pH, decibel, and Richter. The pH scale measures from this very, very small number up as far as 1. Covers a range of 10 to the power 14. And guys, that's where your pH scale comes from, 0 to 14. Decibel scales measures from 20 micropascals. That's the lowest noise a young human like you guys can hear. This is the loudest noise you can hear before your eardrums burst. But that's a very large range of values. And it becomes completely unwieldy to try and discuss noise in terms of these numbers. People just cannot comprehend. Oh, keep your voice down. It's at 187,256,332 micropascals. The numbers just are very hard for our brains to scale. So we use the decibel scale, which simply goes from 0 up as far as 140. pH scale goes from 0 to 14. Then the Richter scale can measure from 10 nanometers up to 10 meters. And the Richter scale then goes from 0, I think, up as far as 10. So we use logs, guys, to reduce these very large ranges of numbers down to much more manageable ranges. And this is where we will start to explore in semester 2. So that's for the future. Okay, folks, that kind of finishes up. So thank you for listening, and we will finish her up there. Thank you.